Hi, I'm Matthew Hilding, and my project is on GPS jamming. So the outline of this presentation will be the introduction, what GPS is, how it works, then you can understand what jamming is, then we'll run through my simulation and the results. First off, navigating the world is an ancient trade, from the first people navigating continents on foot, to the Christopher Columbus era navigating on ships, to present time. And what it started off with was dead reckoning. So dead reckoning is take this heading for this far. How that works is you travel a delta x, which would be equal to the summation of your velocity vectors times the time traveled. From there, if you know you're going from point x to point y, you know your heading, and you know the distance. And then you just get there on your vectors, however it takes you to get there. Then the military came up with a use. If you're on Hawaii and you have a radio antenna, and then you have another antenna on the US, these antennas transmit a signal. Depending on how long this signal gets to you, their delta T, you can find out where you are. But that came with a uncertainty, because this signal will overlap, so you would have to know if you're at the northern overlap or the southern overlap. From there, Einstein's special theory of relativity dictated a time dilation, which gave a relativistic correction to the amount of time that it takes for something to travel somewhere. So your time dilation would come mainly from satellites, which would be delta t over the square root of 1 minus b over c squared. That allowed for GPS to give very accurate coordinates, and then other countries followed suit, came up with their own systems, such as GLONASS. So GPS stands for Global Positioning System, which is a system of about 30 satellites just for GPS. Then there's satellites for GLONASS and the other systems of the world. Depending on how many satellites you can lock onto gives you the amount of accuracy that you can resolve to. So how does GPS work? So let's say you're on this pale blue dot we call Earth. There's an island here, and you're standing in the vacuum of space with a GPS receiver, which don't try it at home. So you're going to have these satellites here out in space, much more than this, lots of space debris, but they are transmitting a signal down to the Earth. That signal carries a message on it. It comes down in two different frequencies called L1 and L2. Those frequencies carry lots of information on where the satellite is in time. So you're going to have an X, a Y, a Z, and also a time component along with it for each satellite. Now when these signals get to the GPS receiver, then this GPS receiver gets all the information from Sat1 and so on, and it calculates its position. So like I said, satellites transmit on two different frequencies, L1 and L2, which are 1575 and 1226 megahertz. It gives the position of the satellite, the time, where it's going, and the position of the other satellites. Then you get trilateration to find your four unknowns, which are your X, Y, Z, and your T. So to get a very good three-dimensional spatial resolution, you need at least 4 satellites. So how does it get this trilateration? Say you have 3 satellites here, and each satellite transmits a signal. Now on this wavefront, it takes delta t to get to you. So from here you have one satellite there, and there's another satellite transmitting here. This satellite also gives out a signal of delta t. Now from here, you can be either in this intersection or this intersection. Then you need a third satellite giving out a delta t as well. When you get that third satellite, then you can disregard this one, and this is the location that you're at this intersection. So what is jamming? Jamming is blocking a receiver's capability to receive the satellite's message. Now when the satellite sends the message down to Earth, it loses about 180 dBs worth of energy just from free space path loss and atmospheric loss. So the signal that's received is below the natural noise threshold, and the receivers pick the signal out of that. Now, the best way to jam this is to jam with an added white Gaussian noise on the frequencies L1 and L2. And it just has to be more powerful than 165 decibels. So here we'll get into the simulation. The waves that I used were 2 sine waves, one being GPS, the other one being the jammer. The jammer is just 1/4 to the end of the simulation using a sine wave. I mean, the GPS starts to end. So here's the simulation. This one right here is the GPS. This is the receiver. And down here is the jammer. So the GPS signal is on right now, and it's transmitting with an amplitude of 1. The amplitude of the jammer is going to be 3. Now here you're going to see the jammer overtake the GPS signal just because it's at a higher dBW. The axis that you see on the simulation here are 0 to 1000, because if I went any higher than that, MATLAB couldn't handle it. It couldn't handle a real life simulation. So I downscaled it just to simulate and model what would happen on a large scale environment. So now the receiver only sees the jamming signal because the GPS signal is too weak to reach the receiver. It is now in the noise region. Then we'll skip through the simulation. It just stays like that for the rest of it. So for the results, this is what the receiver sees. So as you can see here, this green line is when the receiver started to see the signal. And it was only this strong. Then the jammer came in and took over. So now this is what the receiver sees. And now it's not tracking. This is very important to, say, the Department of Defense, because if somebody can come in and jam the signal of the fighters or jet aircrafts, then it is going to be detrimental to the mission. So this is a very hot new topic in the Department of Defense, and a lot of research money is going into this. And that is going to be my project for the semester. Thank you.